Hi, this is problem 2.28. Here we are dealing with a nitrogen gas. So this is the type of liquid that we're dealing with, gas, within a piston cylinder assembly undergoes a compression. So what does a compression mean? Compression tells us that the gas pressure will increase. So from state 1, the gas pressure or nitrogen pressure is 0.2 megapascal. The nitrogen gas volume at state 1 is 2.75 meter cube to a state where the nitrogen gas at state 2, its pressure increased 2 megapascal. Now the relationship between pressure and volume during the process is PV to the power 1.35 equal constant. Whenever we see a polytropic process, it means we are asked to find work in a variable pressure system. The N value, or the 1.35, which is the polytropic index, depends on the thermodynamic process. So for example, if the polytropic index is 1, it means that we are dealing with a isometric, I forgot, which means a constant temperature. And what does this relationship tells us? That the pressure at state 1, which is 0.2, when you multiply it by the volume at state 1, it will give you a certain number. That number will be the same when you multiply a different pressure with a different volume. It will give you the same constant. So that's what this relationship tells us. Now for the nitrogen, we are asked to determine the volume of this nitrogen at state 2 in meter cube and the work of this whole process where we go from state 1 to state 2 in kilojoules. So the first step we have done it, we read the problem. The second step is to write down what is given. So here we are given pressure 1, 0.2 megapascal, volume 1, 2.75 meter cube. This gas, from this state, it went under compression. This gas is inside the piston cylinder assembly. The piston compresses the gas and it increases its pressure to 2 megapascal. And we are told to find the volume of the gas in this state. And when the gas goes from state 1 equilibrium state to another equilibrium state, we are asked to find what is the work done or the energy required to do for the piston to do that compression in kilojoules. So this is the second step that we have done in here. We wrote down what is given to us. Now let's try to sketch this problem using a graph. So the problem will become more clear to us and will help us solve the problem much better. So let's draw a vertical axis. This vertical axis is the pressure. And as we go up, the pressure increases. And here we draw a horizontal axis, and this axis will represent volume. And as we go to the right, the volume increases. We started pressure 1 at 0.2, and the volume is 2.75. So here we drew a point. This is state 1. Now in state, it went to a state 2 where the pressure increased with 2 megapascal, and as we compress, the volume will decrease. And we want to find the volume in state 2. And as you can see, this is the path that the gas takes to go from state 1 to state 2. And this path, its curve path, depends on the polytropic index. So every polytropic index will give you a different curved line. And the path goes from the right to the left. So that tells us that we're going to have negative work because we go from right toward the left. So when you go toward the left, negative work. When you go toward the right, you're going to have a positive work. and we are asked to find the work between state 1 to state 2, which will be the area under the curve. And this curve, it's the points of this curve is generated from this relationship. So that's what we need to find in here. And as we said, this is our main equation. This is a polytropic index. And therefore, since PV to the power 1.35 equal a constant, so that tells us when we multiply B1 V1 to the power 1.35 at state 1 will give you the same constant as P2 V2 to the power 1.35. So this is a very good important relationship, so we can that will help us solve for volume number 2. So here we wrote down again this relationship, and here what we want to do is we want to find volume 2. So here we will move P2 to the other side of the equation, and now it's a matter of inserting the values to get what we want. Now here the power is to 1.35. So here what I did is, in order to get rid of this, and this is by knowing exponent rules, to get rid of this, we will take a to the power 1.35 to the power 1 divided by 1.35, because this will cancel with this, because in exponents, when you take something to the power, you multiply it. So that's exactly what we are going to do in here. All to the power 1 divided by 1.3, and also the same thing on the other side. And here we will place the given values. So 1.35 and 1.35 will, when you multiply these two, will give you volume to the power 1, which is this one right here. And this one will be all the way to the power 1.35. And now the megapascal will cancel with the megapascal. We will plug this into our calculator, and it will give us this value. So the second value, 0.5 meter cube. Well, does that make sense? Volume 1 is 2.75, and we are told the gas is being compressed. So yeah, that does make sense. The volume is supposed to decrease. And this is the answer for A. The next thing we are asked to find is the work. So what is work? Work is pressure times the change in volume. All right. So here, the work from state 1 to state 2, we said that we will take the area under the curve. And the curve is represented by the relationship that we have. Now, we know that pressure is times volume will give you work. So we will take the integral since we talked about area under a curve. So now V to the power n equal constant, and the reason why I used n in here, because we want to find an equation that we can use to find any work for any polytropic index. So what we will do in here, we will solve for B and move V to the other side of the equation. And that's what we did in here. So now we will take this and plug it back into our integral and change the B with the relationship BV to the power n equal constant, where n is a polytropic index, and it can be any number. For example, what we have in our problem is 1.35, but we want to find an expression for any polytropic index number. So here, what we will do is we will go from volume 1 to volume 2, and we replace the pressure with the relationship that we were given, dV. So we will take the constant outside the integral. So now this is basic integration that you need to do. So using integration rules, v to the power minus n will give you minus n plus 1 divided by minus n plus 1 from volume 1 to volume 2. And then we will subtract volume 2 with this expression minus volume 1 with this expression. That's what we did in here. And in the denominator, we rewrote this as 1 minus n. Now, when we go back to constant, so what is constant? So if you go back to this problem, this expression, you can solve for the constant, or this one. Constant is bv to the power n. And we will take the constant and distribute it. So the b2 v2, b1 v1 to the power n, this is the constant. So now what we will do is we will take this and we will use the exponent rules. The exponent rule, or it's called the product rule for exponents. So when we have a to the power m times a to the power n, it will be equal to a to the power m plus n. So a in here represent v sub 1 or v sub 2. The m represent n, and the n represent minus n plus 1. So in here we can say n plus minus n, or n minus n plus 1. So n minus n is 0. So that's what we did in here. So now we can rewrite this as p2 v2 minus p1 v1 divided by 1 minus n. So this is the general expression that we can use to find any polytropic index. And the polytropic index that is given to us in this problem is 1.35. So work from 1 to 2, this is the expression that we found. So now what we will do, we will plug in the given values and the values that we found. We found value for volume number 2, which is 0.5. And don't forget to mega means 10 to the power 6. Plug this into your calculator and it will give you minus 1.285714 times 10 to the power 6 joules. But we are asked to find in kilojoules, so we will divide this by 1,000. So it will give you minus 1285.714 kilojoules. Next problem, it tells us that we have an oxygen O2 gas within a piston cylinder assembly undergoes an expansion. The previous problem was compression. This problem is expansion. Expansion means the volume will increase, the pressure will decrease. From a volume of 0.01 meter cube to a volume 0.0 meter cube. The relationship between pressure and volume during the process is pressure is equal to A v to the power minus 1 plus B, where A is a constant equal 0.06 bar times meter cube, and B is equal to 3 bar. For the oxygen, determine the initial and final pressures, each in bar, and the work in kilojoules. So let's write what's given to us. For pressure 1, we don't know it. That's what we need to find. This is the initial pressure. The initial volume is 0.0 meter cube. This oxygen gas at this state will be expanded. So the relationship between pressure and volume going from state 1 to state 2, we'll use this expression where A and B are constants. Oxygen pressure at state 2 is what we need to find, which is the final pressure. And the volume of oxygen at state 2 is 0.03, which expands more than 0.01. And we are asked to find the work from state 1 to state 2 in kilojoules. And we are given the two constants, the A and the B, with these given values and these given units. Same thing as the previous problem. We're going to draw the what we have, so we can have a better idea on what we are dealing with. So pressure 2 will be, because when expansion happened, the pressure decreased. and volume is 0.03. Now, and so pressure at state 1, that will be its volume right here, and this is state 2. So, and this path doesn't really represent exactly the path of this expression, but it's close to it. And this one represents the path that the oxygen gas takes to go from state 1 to state 2. And as you can see, this path goes to the right, so it goes from the left to the right. So that tells us that we're going to have a positive work. And the area under the curve will be the work from state 1 to state 2. And since we talked about area, so that means we can use integration to find the work. So this is the expression that's given to us. And these are the given constants. At state 1, this is the equation. Pressure 1 equal A V to the sub 1 to the power minus 1 plus B. So now let's plug in what we have. So this is our A value, 0.06 bar times meter cube divided by, we can V to the power minus 1. To get rid of the minus 1, we can just, from multiplication, it can go down to division, just like that, plus 3 bar. So here the values are given to us. So pressure 1 is 9 bar. This is an answer for number A, letter A. At state 2, pressure at 2 is equal A V2 to the power minus 1 plus B. We will do the same thing as we did in the top. We plug in the correct values. And that will give us that pressure 2 is 5 bar. All right. So now what we want to do is we want to find the work. We know that work is pressure times volume. Pressure is given to us as what? Pressure equal to A V to the power minus 1 plus B. So we said that the work is the area under the curve, so that means we can use integration from volume 1 to volume 2 and integrate work, which is pressure times volume. And what we did in here is we replaced pressure with this expression, which is the expression that is given to us. So in this case, this will be integration rules. 1 divided by x will be ln x. So in this case, 1 divided by v, it will give you ln v. And the derivative of a constant will be b times v, from v1 to v2. And now we will subtract, we will take this expression, substitute it with v sub 2, subtract it from v sub 1. And that's what we're going to do in here. So now we will open the parentheses, and that's what we're going to have in here. So now, as you can see, we have A ln V2 and we have A ln V1. And here B, V sub 2, and B times V sub 1. So these are the common terms. So here we have rules of logarithm. So we know that ln m divided by n equal to ln m minus ln n. In this case, ln m represented by ln v2 minus ln n, which is represented by ln v sub 1. So we can rewrite this green with this rule of logarithm. So, and they have the common, which is the a constant, ln v sub 2 v sub 1 plus b, we can take the common, and it will be v sub 2 minus v sub 1. So that's what we did in here. So now what we are doing is we are replacing the values that we found, and that will give us work 0.1259 bar meter cube. So question in here, what is work? Work is pressure times volume. Pressure times volume. Bar is a unit of pressure. Meter cube is a unit of volume. Now we know that 1 bar is equivalent to 1, 2, 3, 4, 5 to 100,000 Pascal. That's 1 bar. So from the definition of work, 1 Pascal times meter cube, or in other words, 1 joule, or 1 Newton times meter. Now, Pascal is Newton over meter squared times meter cube equal to the same thing. Meter squared cancel with this, will give you 1. You will end up with Newton times meter in here. So this one right here, what we want to do is we want to convert it to Newton times meter to get joules. So we know that 1 bar is 100,000 Pascal, right? So 100,000 Pascal, which is Newton times meter, which what we proved in here, Newton times meter, divided by 1 bar meter cube. And this is with what we're given, we can cancel this with this, and we can convert bar times meter cube to joules. And here we divided our answer by 1,000 and to give us 12.59 kilojoules. So this part is tricky because it simply have to do with converting it to the right unit in here. So if your answer is 0.1259 in an exam or a test, you will have the wrong answer because you found you found the work, but you found it in the wrong unit. So problem 2.3. Here we're told that we are dealing with a closed system. So what does a closed system mean? Closed system means that the mass doesn't change. Consisting of 14.5 pound mass of air undergo a polytropic process from pressure 1, 80 pound force over inch squared, and volume 1, 4 feet cube over pound mass, to a final state where P sub 2 is equal to 20 pound force over inch squared and volume 2 to 11 feet cube over pound mass. This one right here, I'm sorry, the specific volume. And right here we're talking about specific volume. We're not talking about volume. So it asks us determine the amount of energy transfer by work in PTU for the process. So here we're dealing with a closed system that consists of this mass, which means this mass doesn't change. And here we're dealing with a gas that undergoes a polytropic process. Now the pressure at 1 is 80. The pressure at 2 is 20. So here what happened? The pressure decreased. So that tells us that we're dealing with expansion. And it goes from 4 specific volume to 11. So there is an increase. So that this tells us that we're dealing with an expansion polytropic process. So here what we are given, the air pressure at state 1 is 80 pound force over inch squared. The air specific volume is 4 feet cube over pound mass. Air at state 2, the pressure decreased to 20 pound force inch squared, and the specific volume of air at state 2 is 11 feet cube over pound mass. So this is an expansion process for air. It's a closed system, no change in air mass, and the mass is 14.5 pound mass. And we are asked to find the work in PTU. So let's draw this problem in a sketch. So here we had the pressure 80 and the volume, specific volume is 4. That's state 1. And here the pressure decreased 20 and the volume increased to the specific volume increased to 11. That's state 2. So as you can see, we're going from state 1 to state 2, and the path goes from the left to the right direction. So that tells us that we're gonna have work, and work is area under the curve And that means we can use integration of the work, which is pressure times volume, to find the area, which in correspond means the we can find the work. So here we know that pressure times the specific volume to the power n instead of volume equal constant. All right. So that tells us that P1 V sub 1 to the power n equal P2 V sub 2 to the power n. And here what we will do is we will move the pressure on one side and the specific volume on the other side. Now here we are given these values, and what we need to find is we want to find the n value. Pressure over 1 divided pressure 2 equal to V sub specific volume 2 divided by specific volume 1 all to the power n. And what we're going to do is we're going to take the natural log on both sides of the equation. So that's what we did in here. And using log rules, the n will go down here. And then we can move ln to the other side of the equation from multiplication to division. And that's what we have in here. And we plug in the values that we are given. And we found that n is 1.37. All right, so here work from 1 to 2, which is pressure times the change in volume, and specific volume is volume over mass. So here work from state 1 to state 2 is what? Is pressure times volume. And when we solve for volume, we move m to the other side from division to multiplication, and that's what we have. Mass times change in specific volume. So work from state 1 to state 2 equal to mass. Mass is a constant. It's not changing. And instead of using volume, here we're using specific volume. And from the first problem, as you can remember, we found an expression which is P2V2 minus P1V1 divided by 1 minus n for any polytropic index except 1. Because 1 minus 1 on the denominator will give you 0. So here we will plug in the values that we have. And it looked like I haven't took this out. So when you plug in what you have, then you can cancel the feet squared with the feet cubed, and you will be left with 1. The feet squared and feet cubed will be left with 1. So right here, this is what we have: pound force times feet over pound mass. That's the unit that we will be left with. And pound mass times pound mass will lift you with pound force times feet. And now we are asked to find it in PTU. So what we will do is we will use the conversion factor, where 1 PTU is equivalent to 778.17 pound force times feet. Pound force cancels with a pound force. And that will give us a work from state 1 to state 2. So simply this problem is easy. It's just the units are tricky, and you need to be careful with dealing with units. And that will be the answer for this problem. Thank you very much.